Hey guys, welcome to my channel. Our circuit for today would be buck converters and boost converters in power electronics. So let's get on with it. First, we'll start with buck converters and then we'll move on to boost converters. There's just a very simple difference between them, which being that buck converters reduce the input voltage while boost converters increase the input voltage. So let's just get the fundamental components. We'll go back to our sim power systems block, power electronics. This time, remember, we are not going to take an SCR, we are going to take a MOSFET or an IGBT. So I'll be using a MOSFET because MOSFET is like the standard for electronics, but IGBT is fine too. This is done because SCR cannot handle uh, SCR cannot turn itself off. So like SCR requires a commutation circuit to turn itself off, while MOSFETs or IGBTs, if you do not apply gate pulse to them, they will turn off. So now we'll go to our handy pulse generator. So there's a pulse, we have a pulse generator, we have an inductor. So for inductor we'll go to again elements, and we have series RLC branch, so that will give us an inductor. So just for inductor you have to do is to just take L, and we'll just use 1,000 or 100 millihenry as our starting value. Now we have a MOSFET, inductor, power electronics, we'll take a diode so that there's no reverse current, and last but not the least we need a supply, so electrical sources and DC voltage source, and that pretty much sums it up, I guess. So you can keep supply at whatever amplitude you want. Let's keep it at 100, let's keep it at default. Okay, so for buck converters, the MOSFET would be in series with the supply. So remember that drain would be connected to the positive, not the source, because there is an internal diode which has to be reverse biased. And we have our RLC branch, which is L inductor for now, and pulse generator connected to MOSFET. Diode which this diode would be acting like a freewheeling diode right now. So this diode is just for the purpose of freewheeling action of the inductor, and that's our ground. And we'll have to add a capacitor. We'll go back to elements. We need a capacitor and a resistor. So this capacitor is the storage element of our buck converter. So it's like this capacitor would be the person who would be storing the output voltage and keeping it constant while the inductor does its job. So capacitor, we keep it as standard 1000 microfarad. That's the standard that's being used. Now that there is polarity, we'll try to maintain it according to the polarity. And this is the negative polarity of the capacitor. This is an electrolytic capacitor. Control R. And we have a resistor connected to the load. And this is just the resistor. We'll keep it as 100 ohms, 100 ohms for now. Okay, so we are done with our basic blocks. Pulse generator frequency, we will have like we'll have a good frequency. I don't know what that calculates to, but I would recommend you all to calculate the frequency. And that's what pretty much sums it up. Now we need measurements, and so for measurements we have as measurements, we need a voltage measurement. Okay, we're not getting it. Voltage measurement. Okay, we have a voltage measurement, it's in measurements. Okay, voltage measurement, and we even require current measurement. Current measurement, we'll do it later, and then we need a trusty scope. We have a scope. There it is. Big and huge for now, and we'll increase the axis to about 3 to 4. So just keep 4 axis for now. So this is our voltage. Our first job would be to calculate the output voltage that is across the load that we are handling. I want to increase the screen size. So, yeah. So we have our trusty old voltage measurement block. Okay. So that's our oscilloscope, and we're pretty much done with this. We'll keep the duty cycle or the pulse with 250% for now. So with 50% duty cycle, what we are expecting our output to be is around like half of the input voltage. So our input voltage is 100, so our output should be half of it, that is around 50 volts. So that's the oscilloscope. Let's zoom in a bit. Okay, so these are the pulses. So if you see, it looks like distorted waveform, but this is not a distorted waveform. This is a very good waveform because we are having an oscillation from 49.570 to 49.570. That's terribly good, like, too good. Axis properties will start from 0 to 50, 0 to 55 maybe, or 60. Let's go to 60. Okay, and this is like a constant voltage that we are getting, and that is 50 volts. If we have it in terms of 100, like this is like, okay, like 100, so this is like half of the input voltage that we were applying. So now we'll be just so this is like the proof of concept that our circuit is actually working. Now we'll just go to various blocks. If you want to check, we can even go check for measurements, and we can go for the mean value, and then we'll go for a display. So display, and then these two and these. So if we have it, our mean block is not configured for that. Our averaging period would be 0.0002, if I'm right. 0.00. Okay. So now we are getting a bit of constant output voltage, that is around 49.5 volts, and that's what is expected value of our output voltage. Now we'll go back to our scope. So what are parameters that we are interested in right now? So we are interested in the current through the inductor. So let's do that. So that is the current through the inductor that we are getting, and then we have voltage current through the inductor and the MOSFET parameters. So So just control and then scope. It's connected. And now we have all our parameters being displayed. The simulation is going a bit slow right now, maybe because of all the parameters that we are adding in. And stop it, I guess. Let's see if we have information. So this is our output. So I don't know why it is oscillating like this, but it's still from 49.5 to 49.8, which is pretty good. And this is our current, and okay, that's our current. Yeah, that's our current, and the current is basically a bit oscillatory from 0.5 to around 0.55. So that's good, I guess. So it's above 0.4, and this is, where did I go? Okay, so this is the MOSFET parameters. So that must be the current through the MOSFET. Pink line. The last one is just empty. So that's how we pretty much sum up buck converter. Buck converter is very simple. Boost converter, if we move on to boost converter, it's pretty simple too. And for boost converter, what we have to do is we just have to change few, you can say few systems over here and there. So boost converter, what we'll do is the MOSFET will go instead of diode. So the drain would be connected where it is, the inductor would be we have to take the inductor from somewhere. Oops, okay, my MATLAB crashed. Okay guys, I'm really sorry my MATLAB just crashed there. So the difference between boost converter from buck converter is that the placement of the coil diode and MOSFET is different. So I just simulated one parameter wherein my inductance is again 1000 millihenry. My diode is the same. I have the same MOSFET with the same pulse generator, that is 0.002. I have mean block with 0.002. Okay, and now that I simulate it, I'm getting around 200 volts over here. And even if I open my scope up, I won't be able to see because it's still doing calculations. Okay, so this is my output voltage is oscillating between 197.5 to 200. So just change the axis properties to from 0 to 200 maybe, and let's make it 400 so that it's easier to see. Okay, and if you see, it's just a line that is 200 volts, so it is staying constant at 200 volts. Even if we have an axis properties over here and we change it to 0 to around 5, and so the current is also a constant current that is being fed in through. So this is how this circuit would perform in real life, and these are the you can say the MOSFET parameters. So this is the current that is flowing through MOSFET at given time. So when the MOSFET is turned on, so if you want to plot, we can even plot the gate pulses. So let's plot the gate pulses to have a better look in how the MOSFET parameters are changing. So have a look over here. At the start there is like this response that you're having by this circuit, and then it stabilizes to a given value. And we again have the same kind of plot. These two are like pretty much clear, I guess. So let's just concentrate on the MOSFET. So these are the operating pulses of the MOSFET. So access properties, we'll take it to like 2 and -1, I guess. Okay, so we have our pulses over here, and this is the MOSFET current and voltage waveforms. So access properties. If you go to C over here, we go from -10 to around 50 is fine, I guess. Okay, now this is much more visible. So the graph in the yellow is actually the current, while the graph in pink is the voltage across the MOSFET. So the voltage across the MOSFET is like it goes up to 200 volts. It is because of the output voltage. So that's what it is. This actually comes down to a fundamental point, that what is the output voltage limited by? The output voltage of this circuit is limited by the handling voltage, or the off-state voltage of the MOSFET. So if the off-state voltage of the MOSFET is breaking down at around 250 volts, there's no possible way to take it above 250 volts. So it is limited by the MOSFET. While in the yellow we have current, which is not quite visible. If we have access properties, go in there and play with some numbers, I guess it should appear. So okay, so we can see this graph in yellow is the current that is flowing. So if you have an observation, half of the time the current is flowing through the MOSFET, while half of the time the current is flowing through the load. So at this point, through the diode, there will be for 50%, since my duty cycle is 50%, for 50% of the time there won't be any current flowing through the diode, while for the other half of the time there will be current flowing through that in such a way that the output voltage would be double of that of input voltage. So this is how boost converter goes. Like we have 100 volts is input and 200 volts is output. The formula is pretty simple. That is, I guess, 1/1 plus duty cycle into the voltage to get the input voltage to get the output voltage. Or is that okay? So that's how it is, and that's what pretty much sums us up with the boost converter. Thank you for your time.